Hi everyone. Our presentation is about approximating dynamic of stochastic gradient descent with SDE. Most of the machine learning problems can be framed as optimization problem. For example, for supervised learning, we are looking for a predictor with minimum risk. Let L denote a predefined loss function and theta denote the parameter of interest. For example, weights of neural networks. Then we have theta star as the minimizer of a function f that is defined as the loss function averaged over the data distribution. And the most popular optimization algorithm to solve this is the gradient descent algorithm. It's a very simple algorithm. First, we randomly initialize theta 0. Then for each discrete time step, we compute the gradient of f theta, and then we update theta in this direction by predefined step size alpha. Then obviously, this is a discrete time algorithm. However, to analyze its dynamic, we can consider its continuous time version and then approximate its dynamic by analyzing its ODE. That is d theta t over dt equal to negative of the gradient f at theta t. There are two popular variations of gradient descent. The first variation is GD with momentum. So in this algorithm, we combine the current gradient with the gradient in the last step. And then we move the theta in this direction. The second variation is GD with natural momentum. So in this algorithm, we first compute the look ahead gradient. And then we combine this gradient with also the gradient in last step. Then we move in this direction. In practice, we do not have enough information about the data distribution. We only have RID samples from it, from which we can build f hat to estimate f. And f hat is defined as the average loss over the samples in the training data set. And its gradient is just the average gradient over the training data set. However, in the latest machine learning applications, n, the number of data, is usually a very large number, and theta is often high dimensional. This can incur significant computation cost because you have to compute the gradient at n training samples. So SGD relieves this problem by approximating the gradient of f hat with a random pair of xy from the training dataset instead of averaging over all the samples in the dataset. We can use stochastic differential equation to analyze the dynamic of SGD. And here we give a motivating example. Let mu theta denote the gradient of the true objective. So mu theta is a vector, it has no randomness. Then we can rewrite the formula of SGD as follows. Equation 7 is the formula for the update rule of SGD. Then we rewrite equation 7 to equation 8 by plus minus mu theta k minus 1. And then we have this extra term, v of theta k minus 1. That is a random vector because the gradient of L at random point xy is also random. So clearly, given theta, the expected value of the random vector v theta is 0. And if we assume that v theta follows Gaussian distribution, and let sigma theta denote its covariance matrix, we can rewrite equation 8 as a time homomodulus SDE, where the negative mu, mu is defined as above, is its drift, and its diffusion coefficient is sigma theta t, where theta t is just the square root of the covariance matrix of v theta. And Wt is just a standard Brownian motion. Before we get into the proofs, we quickly present the mathematical concepts we will use in the following presentation. We first define polynomial growth. A function gx is of polynomial growth if there exists positive integers kappa 1, kappa 2, such that this inequality here holds for all x in the domain of G. And we denote the set of polynomial growth function as G. And we use G to the beta to denote the set of beta times continuously differentiable functions, which together with its partial derivatives up to and including order beta belong to G. So this means that all the functions in G beta has derivatives that is also of polynomial growth. Then we also need the concept of weak approximation. So let t be a real let t be a positive number. Let eta being zero be in the range of zero and the smaller value between one and t, and let beta be an integer. Set n equals to the floor of t over eta. Then a continuous time stochastic process is an ordered beta weak approximation of a discrete time stochastic process if for every g in the function class of g to the beta plus 1 as we defined right here, there exists a positive constant such that the worst approximation error between between the continuous time and the discrete time stochastic process is less than c times eta to the order of beta. And here c is unrelated to eta. So towards the end of this presentation, we would like to prove that using stochastic differential equation, we can have a weak approximation of the stochastic gradient descent. Now I will move the stage to my teammate Haoming for the presentation.
Thank you, Juncheng, for that wonderful introduction. And now we are going to approximate stochastic gradient descent with stochastic differential equations. But first, I'm going to define a one-step approximation. So recall that a general stochastic gradient descent or stochastic gradient ascent is basically the process of equation 12. And we consider the SDEs in equation 13 to be the approximation candidate. And we assume some classic assumption that B and sigma are uniformly linear growth and B and sigma is uniformly Lipschitz for the equation 13's SDEs. Now we define a one-step changes for the stochastic gradient descent process and also the SDE approximation to be equation 14. Then using all of those definitions that we have shown before, Li et al. At 2019 have proved this theorem as the main theorem of their paper to show that the SGDs can be approximated by stochastic differential equation. So the theorem basically have two main conditions. The first condition is that the differences between the S changes is polynomial growth. And then also the one-step changes for each of the processes is also polynomial growth. And then for a second condition, we need that the moment of the SGD process to be uniformly bounded with respect to k, which is the number of iteration. And then after all of these conditions, we can show that the expected value of g of x for some function g minus the expected value of g of big X, which is the process of the SDE, is a weak approximation. So to prove this theorem, we essentially needs to expand the differences recursively by recursively expanding the g of x tilde k and the g of xk. And then after expansion, we reach this big equation here. And note that the function g has some polynomial growth, and then the moment or the 2n moments are bounded by this k2 function that is also polynomial growth. And the fact that one-step approximation is alpha plus 1 weak approximation, it can be shown that theorem 3 holds. And finally, with theorem 3, all they're left to do is to show that the process of SDEs satisfy the two conditions of theorem 3. And then we have our desired result that SDE can approximate SGDs. And a similar statement can also be used for SDEs to approximate stochastic gradient descent with momentum. So to approximate different SGD, we start with classic SGD that we approximate by using dxt equals the negative gradient of f of x dt plus some diffusion term. And note that the f of x here is essentially the loss function we have in the optimization scenario. Sigma is the expected value of gradient of gamma f of x, subtracting from the gradient of f of x, multiplying with its transpose. And gamma here stands for mini batches or the IID samples taken from the population. to calculate the gradient. And then for SGD with momentum, we add an additional momentum term as mu of Vt. And then for Nastrov accelerated momentum, we have not only just the Vt here, but we also have a second order term that is sort of like the acceleration. Note that all of these have the same diffusion coefficient, or essentially the same diffusion coefficient as sigma x of t defined here. Then finally, Li et al. Showed some simulation result. We taken only 2 of those. And what is being shown in these 2 plots are learning rate matters a lot. For example, on the right-hand side, we see that if the learning rate is big, the mean of the processes deviates away from the 25 to 75 percentile of man processes. And also on the left-hand side, we show that SGDs can be approximated by SDEs well, but also it is always dominated by some huge deviations if the learning rate is not set correctly. Finally, we move to some other related topics of SDEs and SGDs. First, people can show that implicit regularization can be derived by analyzing the stochastic differential equation parameterization of stochastic gradient descent. And also, people in differential privacy developed noisy gradient descent for machine learning that utilizes random noises to achieve information privacy. And this is another case where noise exists in the gradient descent process. Thank you. And this is the end of our presentation.